Do you ask yourself, what would Jesus do every time you have to solve a math problem? Perfect. We can help you avoid calling the Lord's name in vain by watching this here video by Fort Bend Tutoring and Mr. Witt.
Hello ladies and gentlemen, this is Mr. Witt with Fort Bend Tutoring, and today's tutorial is going to be about solving variables when dealing with equal matrices. That's right, equivalent matrices. Alright, and this is the format that we're dealing with. Anytime you have equivalent matrices, there are two conditions that must be met at all times. The first condition is that the matrices must have the same dimensions. What does that mean? That means that the matrices must have the same number of columns and rows. So for instance, what we're dealing with now is a 2 by 2 matrix. That's right. I have 2 rows in this matrix and I have 2 columns in the matrix. The rows are the horizontal entries, okay? Whereas my columns are the vertical entries. Yeah. So this is a 2 by 2 matrix. It has to be set equal to another 2 by 2 matrix. And the way equal matrices work is that every element within the matrix has to be equivalent to its corresponding element in the other matrix. Yeah, that's what we're going to be focusing on in this video. And to take this point a step further, you need to know that in our example right here, that A must equal to E, that B has to equal to F, that C has to equal to G, and that finally D must equal to H, because they're all in their respective places, their corresponding places within the matrices. All right, and we have this big equal sign right here. You can't ignore that. You can't ignore the equal sign. All right, so let's go ahead and solve for some variables in equal matrices. All right, here we have it. Problem number 1. It says solve for your variables x, y, and z. And here what I have before me is a 1 by 3 matrix that's set equal to another 1 by 3 matrix. What I mean is that I have one row right here, and I have 3 columns. Yeah, 3 columns. And this is set equal to a matrix that has 1 row and 3 columns. Yeah, all right. So because those two conditions have been met, and we have that lovely equal sign in the middle, we can go ahead and set each corresponding element equal to one another. For instance, I can say that 2x must equal to 5. Why? Because the element that you'll find in the first row and in the first column, in other words, this 2x, has a corresponding element in the second matrix that is also in the first row and the first column. Yeah, so they must be equal to one another. Every element in the first matrix has to be equal to its corresponding element in the second matrix. That must be the case. So I can set the equation 2x equals to 5 and then solve for x. So I'm going to do so by dividing both sides by 2. And I find, all right, that x must equal 5 halves. All right. That's the value of x. Next, let's go ahead and solve for the other 2 variables. So the next equation that I'll set up will state that 3 must equal 3y. So that's my second equation in order to solve for the variable y. And all I have to do is divide both sides by 3, that coefficient in front of the variable y. So that y equals 1. There you go. Y equals 1. Yeah, 3 divided by 3 is 1. I know you know that. Now, finally, we're looking at that third element here in our original matrix, right? In that first matrix, the element 3z, that must equal to what value? What did you say? What? You crazy. Really? Exactly right. It has to equal to 9. It must equal to 9. That's right. So our equation will be written as 3z equals 9. And we'll go ahead and solve for that now. So I'll be dividing both sides by what number? Say it. Scream into the screen. Yes, you're right. Very good. Z equals 3, and we have our 3 variables solved for. That's right. You could even write this as an ordered triple. All right. So you could say that your first value is 5 halves, the second value is 1, and the third value is 3. Each of these values corresponding with x, y, and z as an ordered triple. You could do that. All right. So either of these forms of the answer will suffice. And as always, we're going to red box our answers, ladies and gentlemen. That's right. We like to show off for our teachers and our classmates that we know how to find the right answer. And here's that ordered triple. There you go. just like that. So 5 halves, 1, 3. These are the solutions to the variables for problem number 1, and done. Let's go ahead and move on to problem number 2. All right, here we go. Center that screen. There you are. In problem number 2, we're asked to solve for x and y. All right. In our first matrix, we have a 1 by 2 matrix. That's right. We have 1 row and we have 2 columns. That's what we have. That's our first matrix. In the second matrix, we have 2 rows and we have 2 columns. All right. So are these equal matrices is what we need to find first. Because if they're not, that means we can't solve this problem. If they are, then we can go ahead and start setting up their corresponding elements equal to one another. So can we solve this problem, ladies and gentlemen? Can we? No, we can't solve this problem because the dimensions of our first matrix is a 1 by 2, and it's being set equal to a 2 by 2. That means that these matrices cannot equal to one another. There's no way they're going to be equal to one another. Therefore, there's no solution to this problem. You can't solve it. No, you can't solve this problem. Okay. Yeah. Oh, I'm sorry. What do you want to see? You want to see no solution? There you go. You can put the null set. There you go. Or you can just write out no solution. All right, that'll work as well. You can just put that there. Okay. All right. There you go. So yeah, here we go. And of course, we need to red box this. Red boxing it. Either the null set, or you can just write out no solution. Because these are not equivalent matrices. So therefore, we can't set their corresponding elements equal to one another because they don't have corresponding elements for half of the things you see there. All right, so that's problem number 2. Moving on. Here we go. Look at this nonsense. Look at this nonsense here. I can't even get it all in the screen. Problem number 3, it says solve for all variables. Solve for all variables. And we have quite a few, don't we? But the first thing we need to verify is whether or not we have equal matrices. We need to see if this matrix can be set equal to that matrix based on the fact that their dimensions are the same. They have to have the exact same dimensions. So what I see in this first matrix is 3 rows, okay? Well, I see 3 rows. And I also see 3 columns. All right, so that means that this is a 3 by 3 matrix. Let's just go ahead and make note of that up here. Okay, and it must be set equal to another 3 by 3 matrix in order for us to solve for the variables in this equation. So the second matrix has 1, 2, 3 rows, yes, and it has 1, 2, 3 columns. Interesting. That means that we can actually set each corresponding element equal to one another. So that's exactly what I'll do. Let's start by solving for our variable x. Yeah. If we focus on this element right here, the one that says 3 plus x must be equal to what value? Do you know? Can you see it there? Is it all in view for you? Exactly. It has to be set equal to 9. Very good. So in solving for this, we can just subtract 3 to both sides, right? There you go. All right. So my 3's will cancel out here, and I'm going to go ahead and bring down that variable x, and 9 minus 3 is still 6. It is still 6, ladies and gentlemen. That's the value of x. All right, great. Now let's solve for y. Okay, where is your variable y? What element contains your variable y? Wouldn't it be this element right here? In other words, the element that can be found in the second row in the third column. Exactly. Yeah, so if we set that y plus 1 must be set equal to what value? What's the corresponding element? Exactly. It has to be set equal to that 9 over here that's also found in the second row and in the third column. Very good. Very good. So we'll be solving for y now. So I'm going to go ahead and subtract 1 to both sides here. Okay. And the 1's will cancel out. All right. And y equals to 9 minus 1, which is 8. That's right. Using the addition property of equality, ladies and gentlemen. Isn't it lovely? Is it not lovely? Thank you. Next. Let's see here. Let's solve for z. We did x first and then y. Let's go ahead and go for z now, right? So solving for z, we'll have the element here in that second matrix, that second row, first column, that z plus 3. Z plus 3 must be set equal to what value? Do you know? Do you know? What's the corresponding element for the second row, first column? It'll be the number what? Exactly. It must be the number 5. Very good. Very good. Let's go ahead and solve for that. So in order to solve for Z, I'll need to use the additive inverse of positive 3 here, which is negative 3. So in other words, I'll be subtracting 3 to both sides. All right. And my 3's will cancel out on the left side of the equal sign. I bring down my variable Z here. And 5 minus 3 is always 2. All right. So Z equals to 2. However, that only takes care of 3 of the variables that we have in this problem. And we have a lot of variables in this problem, don't we? All right. So let's go ahead and move on to the next page here. All right, so continuing problem number 3, we've already taken care of the variable x, we've already taken care of the variable y and z. I think the next variable we should solve for is w. Let's go with w, all right? So I'll have 8 minus w, and that must be set equal to what value? What's in the same location as 8 minus w, that element that you'll find in the second row and in the second column? Right. That's right, it has to be w, because w is also in the second row and in the second column. So 8 minus w must be equal to w. So now we'll go ahead and solve for w. So I'll be adding w to both sides of the equal sign here. All right, my w's will cancel out. I'll bring down 8, which now equals to w plus w, which is 2w. Right? From here, we'll go ahead and divide both sides by the coefficient of 2. And 8 divided by 2 is always 4. All right, trust me on that. Okay, so w equals to 4. Okay, that's that variable. What's next? What's the next variable you want to solve for? All right, did I hear somebody say n? N? All right, let's go with n. All right, so be it. Let's do n. So here with n, I have n equals to what value? It has to be an element that you would find in the second matrix that's located in the first row and in the third column. What value is that? Well, here's my first row in the second matrix over here, right? And the third column is 1, 2, 3, so it's going to have to be 6. Yeah, so n equals to 6. N equals 6. I can't do anything else with that. N equals 6 and done. I didn't even have to solve for it. I like problems like that. Matter of fact, speaking of problems like that, let's go ahead and solve for p. We'll just set it up right underneath n. We'll say that p equals what value? P equals to what? It has to be a corresponding element that's located in the third row and in the first column. So what value would that be? Exactly this value right here. It has to be negative 4. It has to be negative 4. You guys are doing great. I'm so proud of you. So proud of you. Good stuff. Let's find another easy problem. All right, I'm loving the easy problems. So we took care of n. We just took care of p. Let's go with q. Let's go with q, right? For the variable q, q has the equal to what value? Do you know? It has to be an element located in the third row, second column. Third row, second column. So here's our first matrix here, right? This is the first row, second row, third row. This is the first column. This is the second column. Bingo, it has to equal 3. Q equals to 3. I love these problems. I love them. They're so cool. I hope I receive 5 of these problems for Christmas and my birthday. And just any holiday, because these problems are fun. If you want to send me a gift, you can send me a problem just like this. There you go. Thank you. And I'm saying thank you in advance. I appreciate you sending me a problem just like this for me to solve, because I love these problems. They're too easy. So next, we've taken care of x. We've taken care of y. We've taken care of z. We've taken care of w. We've taken care of n. We've taken care of p. We've taken care of q. So we need to take care of r. Right? We need to take care of r. An element that contains the variable r is located in the third row and in the third column. Yeah, it is. It's right here. So that means that any corresponding element that is also located in the third row and in the third column can be set equal to it. So here's my equation. I can say that 2r equals r. There's my equation. 2r equals r. And now to solve for r, I'll be subtracting r to both sides of the equal sign here. Okay, so what happens is on the left side, 2r minus 1r gives me r, and r minus r on the right side of the equation is 0, so r equals 0. There it is. That's it. That is it. I am so red boxing my answers now. By red boxing w, that equals to 4. Yes, that's a w, I know it's ugly. And we know that n equals to 6. Thank you. We know that p equals negative 4. There you go. There you go. We know that q equals 3. That we do. And we know that r equals 0. Yeah. Let's go back and get those other three variables. So now that we've made it back to the first page of problem number 3, we know that x equals 6. Yeah, and we also know that y equals 8. And we know that z equals 2. So these are all the variables that we solved for in problem number 3. Oh my God, that had a whole lot of variables. All right, so that's problem number 3. Let's move on to problem number 4. Come on. All right, we have problem number 4. It says to solve for all the variables. Anytime it says solve for all variables and they don't even like list the variables, like saying solve for x or solve for y, you know it's going to have a whole lot of variables. All right, scary stuff, right? So in this problem, we have a different format here. All right, and I'm sorry I had to stack these, but what you see before you is the sum of two matrices on the left side of the equal sign that equals to this matrix on the right side of the equal sign. Yeah, so you have two matrices that are adding to equal this matrix right here. So the first question you should ask is, can this be done? Well, anytime you're adding or subtracting matrices, as these are attempting to do, they must have the same dimensions. All right, so let's check out this first matrix. This first matrix is a 2 by 3 matrix. See, it has 2 rows and 3 columns, right? And it's attempting to add to another matrix that also has 2 rows and 3 columns. Well, that's okay. You can do that. You can do that. That's all right. And it must equal to another matrix that also must have the same dimensions. And this matrix right here, it has 2 rows and 3 columns. So it's okay. Yeah, it's okay now. That means that this is possible. We can work this out. All right. So let's keep in mind whenever you add or subtract matrices, they must also have the same dimensions, and the corresponding elements will add or subtract depending on what operation you're doing. So in this matrix, all right, you can solve it several ways. You could start out by just simply combining these two matrices here and adding them together, or you can do what I'm going to do. And that is, I'm just going to set up an equation based on the corresponding elements. Are you ready? Because I'm about to show you. We're going to start with the element found in the first row and in the first column. So I'll be able to set up an equation that reads a plus 2 plus 3a equals 10. I'm able to set this up because I'm using all of the elements that I'm finding in the first row and in the first column combined with the operations that you have in the equation. So what that means is I'm taking a plus 2 plus 3a to equal 10. And that's how I came up with my equation. I'm going to use this same process to solve for every one of the variables in our problem here. All right, so let's go ahead and solve for this one. We're going to start by combining our like terms here. So I know that a plus 3a gives me 4a, right? Plus 2, which equals 10. From here, I'm able to subtract 2 to both sides. All right, okay. So now I know that 4a equals 8. So now I'll be dividing both sides by 4, and I'll find that a, it equals 2. All right, let's go ahead and red box it. Red boxing it. That's our solution for a equals 2. Now let's continue with the other variables. All right, and now for our next variable. What variable do you think we should solve for next? We solved for a already. So let's go with, oh, y'all want to go in alphabetical order? Okay, that's cool. We'll do that. Let's go ahead and solve for k then. All right, so solving for k, that means that we'll be focusing on the elements that are located in the second row and in the first column, all right? So we're going to string together all of these elements using the operations that we find in the original equation to set up our equation to solve for k. All right, it looks like this. We'll have 8k plus 2k equals 10. All right, so we were able to pull every corresponding element in the second row and in the first column, along with our addition sign and our equal sign, to piece together our equation that we can solve for now. So that being the case, let's go ahead and combine some like terms and solve for this. So solving for k, we have 8k plus 2k. That's going to give us 10k. And 10k equals to 10, ladies and gentlemen. So I'm going to use the division principle of equality to divide both sides by 10 and solve for our variable to find that k equals 1. Yeah, 10 divided by 10. That's 1. All right, there you go. Red boxing it. Red boxing it. Yeah, there you have it. There's our solution for k. Let's continue. All right. You guys said that we were going to do this in alphabetical order, right? So that means that our next variable that we're going to solve for is m, as in Mary, or as in yo mama. Okay, so we have 5m plus 5m equals to 80. So solving for m, we're going to be setting up an equation based on the corresponding elements located in the first row and third column. Yeah, I just couldn't miss the opportunity to make a yo mama joke in a math video. I mean, who does that, right? I mean, seriously, who makes a yo mama joke in a math video? I do. So you have 5m plus 5m. You're going to combine those like terms, all right? So there you go. So we end up with 10m. That's right. Just combine those coefficients together. The variable remains the same. You do not change the exponents on the variable when you're combining like terms. I'm going to bring down 80 here, all right? And next we'll be using the division principle of equality and dividing both sides by the coefficient of 10. This is going to isolate my variable m. Yeah. So the 10s cancel out, and m equals 8. There you go. 80 divided by 10. There you go. Red box it. Red boxing it. There you go, ladies and gentlemen. Oh, we have another variable, don't we? All right, let's solve it. Let's go ahead and solve for the variable z, right? So the variable z can be found right here. All right, so we need to put all our focus in all of the elements located in the first row and in the second column, because that's where you'll find your variable z. So the equation that will form from that is going to be 1 plus 2z, which equals negative 14. All right, you hate that 4? I hate it too. Let's fix the 4. That's a much better 4, right? There you go. But I hear you talking about that z though. I hear you talking about my z. I'm not going to fix it. No, it's going to remain the same. No, I'm not going to fix it. All right, it's going to stay the way it is. I know it's ugly, and it's fine. Fine, Lord, yes. Just okay. That's no better. Okay, fine. All right, is that a better Z? You still don't like that one. It's staying. It's staying. I'm gonna keep that. All right, I'm keeping this Z. I'm gonna start by subtracting one of both sides of the equal sign. Thank you. I'm bringing down my 2Z, which equals negative 15. All right. From here, I'm going to divide both sides by 2. All right, so dividing both sides by 2, I'm going to keep my answer as an improper fraction. If your teacher prefers you to change your answer into a mixed number or a decimal, then do so. All right, but I'm going to keep mine as an improper fraction. So this negative 15 divided by 2, it's just going to remain as negative 15 halves. There it is. All right, and there's our solution. Red boxing it. There you go. That's going to finish this problem now. We solved for A, we solved for K, we solved for M, and we solved for Z. All right, so those are all the variables in our problem here. All right, and we're moving on to our next problem. All right, ladies and gentlemen, we now have problem number 5. And in problem number 5, it says for us to solve for x and y, and what we're given two matrices that have dimensions 2 by 1. All right, so this has 2 rows, 1 column. 2 rows, 1 column. All right, so that being the case, we can set up equations based on the corresponding elements. And what you'll end up with is the following equations. You'll have 2x equals y, and you'll also have 2x plus 3y, which equals 12. So these are our two equations that we formed from our equal matrices, all right, from our equivalent matrices. So when you see a system of linear equations like this, well, what should come to mind first and foremost are the main three ways that you can go about solving this. And that would be the substitution method, elimination, aka the addition method, or the graphing method, which sucks. So we're going to go ahead and I'm going to use the substitution method because we already know what y equals to. Yeah, y equals 2x. They're telling me. So that means I'm going to replace every y in the second equation with 2x. All right, so here we go. So I'm going to have 2x plus 3 times 2x because that's what y equals to. And this is going to equal to 12. All right, so here's my equation that I can use to solve for x. All right, from here we'll go ahead and multiply that 3 times 2x to end up with 2x plus 6x equals 12. And let's go ahead and take this to the next page. All right, from here we'll go ahead and combine our like terms. So I have 2x plus 6x, that gives me 8x, which equals 12. And now we'll just divide both sides by 8 and simplify to find that x equals 3/2. There's your solution right there. X equals 3/2. Done and done for our variable x. And now, utilizing this value, we'll go ahead and plug this back into one of our original equations and solve for y. Remember that 2x equals y. All right, that was the first equation that we wrote. And knowing that our value of x equals to 3/2, we can go ahead and replace that using substitution to say that 2 times 3/2 equals to y. Well, multiplying 2 times 3/2, our 2's will cancel out and leave you with a value of 3. So y equals to 3. Yeah. Okay. So that means that as an ordered pair, if you want to write your solution that way, you'll say that the answer is 3/2, 3. All right. So you can present your answer by showing that x equals to 3/2 and that y equals to 3 that way, or you can submit your answer as an ordered pair and write it this way as 3/2, 3. That solves that equation involving equivalent matrices. All right. I think I like the ring of equivalent matrices better than equal matrices. All right. Well, it's the same thing. Here's our next problem. Problem number 6. And in problem number 6, we're asked to solve for x, y, and z. All right. And what you see before you is a scalar, something multiplying on the entire matrix. See, anytime you have a value on the outside of a matrix, that is called a scalar, and it's multiplying times every single element within the matrix. You could multiply every single element times this scalar of x if you wanted to. Yeah, you could do that, but I'm not going to do that. No, because see, that's going to mix up some variables and stuff. It's going to be real ugly. So our alternative is to notice that in the second matrix, these given values, excluding the variable z, all have 3 in common, don't they? They're all multiples of 3. So why don't we just do this? Why don't we factor out a 3 from all of the elements here and write it as a scalar? Because we can definitely do that. So I'm going to rewrite this as x times the matrix 4, y, 7, and z, which equals 3 times the matrix 4, -5, 7, and z divided by 3. All right? And we can write it this way because factoring is associated with division. And if you multiply 3 times z over 3, you would end up with z. All right? So it's the same. So that being the case, I think we just solved for x, didn't we? We just solved for x. So we know that x equals 3. It has to. It's the same scalar. There you go. And going a step further, we know that y equals to -5. It's the corresponding element. It has to equal -5. So y equals -5. That's awesome. And the next thing that we could do is we can set up an equation saying that z equals z divided by 3. Right. They're the corresponding elements, right? The second row, second column, they have to be equal to one another. So in order to solve for this, let's go ahead and multiply both sides by 3. I think I'll enjoy doing that. All right, like so. So we now have 3z equals, these 3's will cancel out to leave you a z here, and then I'll subtract z to both sides. All right, so 3z minus z gives me 2z And z minus z is 0. And next I'll be dividing both sides by 2. So z equals 0. All right, there you have it. That's our solution for z. So we have all of our answers now. So writing this as an ordered triple, we'll have 3, -5, and 0. So that's our ordered triple. And let's go ahead and red box it like so. All right. So we have 3, -5, and 0. Or you can individually box your variables up to say that z equals 0 and x equals 3 as well as y equals -5 and done. And that's problem number 6, ladies and gentlemen. Just like that. Let's continue. In problem number 7, they want us to solve for x, y, and z. And look at what we have right here. Isn't that cute? Well, being as though we just have a number, all right, as a scalar in this problem, that 4 right here, multiplying on this matrix, I think I'm going to go ahead and just distribute that. All right, so if you don't mind, this is what it's going to look like. We'll have our first matrix here, and 4 times x gives you 4x. 4 times the quantity of y minus 1. I'm just going to write it like this. 4 times the quantity of y minus 1. All right, nothing too fancy. And then 4 times 3, we're going to have 12, and 4 times z is going to give me 4z. So the reason why I want to go ahead and distribute the 4 in this problem is because it's just a number. Whereas in our previous problem, the scalar was a variable. That's drama. Okay, I'm avoiding drama at all cost. So with the number, no big deal. I can multiply everything by 4. It's not going to kill anything, all right? But introducing a variable onto some unsuspecting elements, oh, okay, that's just terrible. Why would you do that to them? That's evil, okay? So you don't want to do that. So that's why I went ahead and just decided to factor out the 3 in the second matrix in that previous problem. But all that to say this, distribute the 4 as a scalar in this problem because it makes it easier, okay? Because it's always about making things easier for me because I'm lazy. I mean, just look at the last time I released a video, right? Been a while, right? Yeah, it's been a while. Because I'm lazy. All right, but I'm working now, okay? All right, I'm working now. All right. So now that we have this is what we're going to do. We have equal matrices. I know this. How do I know this? Because the first matrix is a 2 by 2 matrix. I have 2 rows and 2 columns. The second matrix is a 2 by 2 matrix. I have 2 rows and 2 columns. And I can now solve for my variables by setting my corresponding elements equal to one another. All right. So what I'm going to do first is I'm going to solve for x. All right. And we're going to solve for x by using the elements found in the first row and in the first column and setting them equal to one another. So I'll have 4x equals 20. Just like that. So that being the case, I'm going to divide both sides by 4 to find that x equals 5. Done. We just solved for x. Beautiful, right? Now I'm going to go ahead and solve for z. See, you'll find z over here. Yeah, you will. But notice that its corresponding element has 2 other variables. Why do that to yourself? Don't do that to yourself. Find an easier way. Look at this. Look at the element that you'll find in the second row and in the first column. Look at its corresponding element, 6z. That's easy, right? So we can go ahead and say that 12 equals 6z. That's much easier than that nonsense that we would have had if we would have said 4z equal to x plus y. That's drama. So here I'm going to go ahead and divide both sides by 6. And that'll tell me that z equals to 12 divided by 6, which is 2. There we go. We've already killed 2 of the variables already. That's right. We already solved for them. So I know that x equals to 5. I know that z equals 2 already. Exactly. Now let's go ahead and solve for this final variable here. All right. So continuing on with our setup that we have, we want to finally solve for y. And you're right, ladies and gentlemen. We could use that 4z equals to x plus y to solve for y now because we know what z is and we now know what x is. That's true. But I have a strong suggestion for you. You never want to introduce into your problem values that you solved for unnecessarily. What do I mean by that? We solved for x and we solved for z, right? But I could have made a mistake in that. You could have made a mistake in doing that. So instead, we're going to use elements in the first row and in the second column to solve for y because it's self-contained. It doesn't include any values that we solved for, thus minimizing the chance for a mistake to be made. I could have made a mistake on x, right, when I solved for it. And I could have made a mistake on z when I solved for that. So why do I want to take a chance in introducing a value that I could have made a mistake in order to solve for a third variable? I wouldn't want to do that. So that means that I'll be setting up this equation to read 4 times y minus 1 equals 8. Because notice I have one variable with one equation and I'm not including any values that I solved for. Avoid that when possible. So that means that I'm going to be distributing now. And I'm going to get my arrows popping, ladies and gentlemen. That's right. The distributive property is the king of properties. It is so fun. Love it. Arrows popping. All right. That's what we do here in FBT. All right. So that means that 4 times y is going to be 4y. And 4 times negative 1 is negative 4. And I'm going to bring down that value of 8 because it's cute. That's right. I said it's cute and I meant it. Now we're going to solve for y. How are we going to do that? We're going to add 4 to both sides. Yep, that's me, adding 4 to both sides using the addition property of equality. Thank you, teachers. My next step is to bring down this 4y, which equals 8 plus 4, which is 12. And next, I'm going to divide both sides by what? What's the coefficient on my variable? What is it? It's 4. Very good, Stephen. Good job, sir. We're going to divide both sides by 4 now. We're isolating our variable. So now after simplifying, y equals 3. There you go. So we have solved for all 3 variables. So we can very well write our ordered triple now, right? So what was our value of x? That's right, it was 5. And our value of y is 3. And our value of z is what? That's right, it's 2. All right. There's your solution as an ordered triple. Perfect. All right, let's go ahead and red box it. Red boxing it. All right, so there's your solution as an ordered triple, or if your teacher prefers, you can individually red box your different variables that you solved for. So for instance, y equals 3, and x equals 5, and z equals 2. There you go. So we've red boxed all 3 variables as well as provided our teacher with an alternate solution, which is the ordered triple. There you go. And that's our problem number 7, ladies and gentlemen. Moving on to our next problem. All right. So here in number 8, they ask us to solve for x, y, and z. And check this out. One of our variables is raised to the 2nd power here. Okay, that's going to be fun. So the first thing we want to do is we want to verify that we have the same dimensions. We want to make sure these matrices are equal to one another, that they're equal matrices. Yeah. And how do we determine that? With the dimensions. So what I see in that first matrix is a 2 rows by 3 columns. So it's a 2 by 3 matrix, right? We'll go ahead and state that. It's a 2 by 3 matrix. And we need our other matrix to also be a 2 by 3 matrix. And that is also a 2 by 3 matrix because we have 2 rows and 1, 2, 3 columns. Very good. So based on the definition of equal matrices, every corresponding element has to be equal to one another, which means we can set up an equation that reads x squared equals 25. Because it does. So x squared equals to 25. That means that I'll be using the square root property. So if you're not familiar with the square root property, check out this video right here. Yeah. So moving through the process of the square root property, let's do the following. All right, so we're going to take the square root of both sides. All right, and this is going to be the square root of 25. And because the square root of x squared must be positive, we need to guarantee that by using absolute values. All right, so we'll have the absolute value of x equals to 5. Because anytime you're using the square root symbol, all right, this radical sign right here, you always are going to be taking the principal root every single time. However, solving for this absolute value, we're trying to find a distance from 0 that's equivalent to 5. So we can be 5 places away from 0 at positive 5 or at negative 5, right? Yeah. So that means that your solution could be written like this for x, or you could say that it's going to be x equals to plus or minus 5. All right. Either way is correct. Done and done. And that's the square root property, ladies and gentlemen. You take the square root of both sides, and because the square root has to be positive, you're going to use the absolute value around your x there to guarantee a positive solution here. However, because the absolute value is the distance to 0, and you can be 5 places away from 0 at either positive 5 or negative 5, you end up with plus or minus 5 as your solution for the variable x. I'm going to red box it. Red boxing it. That's x. Now we want to solve for y. And solving for y, that's going to be pretty easy. Yeah, you see that? Yeah, they already have a value that corresponds to y right there. So y equals 9, guys. You know that. All right, where have you been this whole video? It's in the same corresponding place. You can't help it. Red box it. Done and done. And finally, let's solve for z. See, we'll set up an equation that reads 12 equals 2z. But we don't have any room, so we'll do it on the next page. All right, so we have our original problem here, and now we'll be solving for z by setting up our corresponding elements that we'll find in the second row and in the second column. We'll say that 12 equals 2z, and we'll go ahead and solve for it. So I'm going to divide both sides by 2, and 6 equals z. There you go. So as an ordered triple, you can have either -5, 9, and 6, or you can have +5, 9, and 6. All right, so both of these are solutions to the problem, and you can red box that. Red boxing it. Both of these are solutions to the original matrix here for x, y, and z, and you can still individually red box your separate variables. So z equals to 6, y equals 9, and x equals plus or minus 5. Done and done, ladies and gentlemen. That's what's up. So this has been solving for variables in equal matrices, and please rate, comment, and subscribe. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Witt, and Fort Bend Tutoring. Peace.
Thanks for watching. We feel great knowing that you got some help and you're safe and sound. Now, if you'd be so kind as to like this video, subscribe to our YouTube channel, Fort Bend Tutoring, and like us on Facebook. We'd be much obliged.